Earlier, we've been talking about isotopes, different isotopic forms of the same element, and we also talked about the fact that on the periodic table it says how much an atom of that type of element weighs. Well, if isotopes weigh differently, then how do you know which decimal number to put on there? Well, I'm going to kind of talk you through that process, but in order to have that make sense, have to come up with a weighted average, we need to know how abundant each isotope is, how abundant each isotopic form is in nature. So if you have an element that has two or more different isotopic forms, you can look up to see what is the percent abundance of each isotopic form. So, of course, their percent abundances should add up to be equal to 100%, right? Makes sense to me. So their percent abundances are calculated this way, and this kind of boggles my mind. What you do is basically go out and get a representative sample in nature of that element. And then you pick out one of the isotopes, and you count the number of atoms that are that isotope divided by the total number of atoms that you got of the element. So this is all isotopes down here. Okay, and you take it times 100, and that will give you your percent abundance. Make sense? I think so. So here we're going to pick on copper. We have copper mass number 63, copper mass number 65. Okay, of course, I don't have a periodic table in front of me, but we could look up copper. And every copper atom has how many protons? I'll have you look it up. Okay, so we could by difference then go ahead and come up with a number of neutrons. But that's not the point here. Which one of these is more abundant? Yes, the copper 63 is more abundant. If we were to add these up, we get what, 100%? That makes sense, right? Different isotopic forms of copper. Down here we have, so for instance, if you have 10,000 copper atoms, then that means that because it's 69.09%, you have 6,909 of those atoms will be the copper 63. And since you have 30.91% copper 65, 3,091 of them would be that heavier copper 65. Okay. So right off the bat, and we're going to be talking about this in the next part, can you see that since you have more of this one, more of the more of the lighter one, that when you come up with an average atomic weight, it's going to have to be closer to this one. Oh, that makes sense. And we'll kind of do an example of that coming up. So leaving copper, we actually have some more elements up here. We've got neon. Okay, these are all neon, excuse me. These are all about neon. So we have different isotopic forms of neon. We have neon 20, neon 21, neon 22. Now, since there are 10 protons in each, can you see where actually this row comes up with, by difference, the number of neutrons in each isotopic form of neon? Over here on this last column, okay, is actually tells you the relative abundances. So you can see that this, what is it, the lightest one, this lightest one is mostly what the neon atoms out there are. Okay? So down here it kind of says if you again had 10,000 neon atoms, 9,048 of them would be the first isotopic form. Only 27 of them. I was like, are you serious? Only 27 of them would be neon 21, okay, and 925 of them would be neon 22. Okay. So let's see. One more thing before we go on to calculating the. Oh no, I guess two more things. This is a table I thought I had before, an assortment of elements. Here we have neon. We already talked about neon. Hydrogen actually has two naturally occurring isotopic forms and a third man-made isotopic forms. Hydrogen is kind of weird. We have hydrogen 1, hydrogen 2, hydrogen 3. I think it's very weird, actually. They actually have fancy names. So the name of, with mass number 2 for hydrogen is deuterium. For mass number 3, that's the man-made isotope of hydrogen is tritium. That's kind of unusual. Over here then, this column, this last column says what's their abundances. Oh my goodness. See that hydrogen 1 is significantly more abundant than hydrogen 2. And then here, this column, this is what we're going to have to use when we calculate the average atomic weights, okay, is how much an atom of that particular isotope would weigh. So hydrogen 1 would, a weight would for an atom would be this. Hydrogen 2, the weight would be this. Hydrogen 3, the weight would be this. And like we talked about, weights for atoms are in atomic mass units. If we go on down to boron, we looked at boron. We said it had two. We had boron 10 and boron 11. This is then how much 10 and 11 would weigh. This is the relative abundances. Now, if we pick on that one for a minute, notice that the second isotope is significantly more abundant. And we're going to, in the next part, talk about how we get this. But this column right here, this is the decimal number that you see on the periodic table. So for boron, notice it's 10.811. Check this out. Oops. Yeah, 10.811. Notice that this isotopic form is much more abundant than the other, so the 10.811 is much closer to how much that one weighs because it's more abundant. It's called a weighted average that we're going to come up with. We could look at a similar thing. We said with regard to neon that the first isotopic form was much more abundant than the second and even the third isotopic form. So does this make sense when we look at the decimal number for neon, which I was trying to find a little bit ago? The decimal form for neon is much closer to the one that is most abundant than it is towards these guys. Okay, weighted average. All right. One more thing before we go on to the next part is to kind of revisit our copper, two isotopic forms of copper. So we had copper mass number 63 and copper mass number 65. And if we were to go look up how much an atom copper 63 weighs, it's 62.930 AMUs. How much does a copper 65 weigh? It's 928 AMUs. Some problems, and it's not right, but some problems will actually round these numbers to the nearest whole number, and then you get 63 and 65. I really discourage the rounding to use for those average atomic weights to use in the calculations. To use in the calculation they aren't average atomic weights. They are exact weights of that type of isotope. I would discourage you from rounding and using that in AMUs for the next type of calculation we're going to go over.